Hi students, so this is part 2 of chapter 2 in this class. So this will be our second of 12 chapters in the class, and we're at part 2 of that. So if you remember from part 1, we have reviewed the frequency distribution, what that is, why we have it, and how we make one. So that includes regular quote unquote or individual frequency distributions and group frequency distributions. Once we have made tables for these, and because we're doing this for getting all the scores and organizing the scores when we ask people questions about things, we can also show these scores in the form of graphs. So if you have seen or worked with frequency distributions like these, something as simple as how many people scored 1, 2, 3, 4, 5, or answer questions like how many people got A's, B's, C's, D's, and F's in the class, we can also graph that information. So in this chapter, we're going to start with that, how we graph these frequency distributions. And there are several principles and ideas that we need to cover to graph these. So the first thing we want to do is figure out what we need to do to organize that data. Now, if you have worked with graphs before, you know that graphs have two axes. You have the x-axis. There are formal words for these, abscissa, for the horizontal line that has categories of your measurement scales. Here it could be F, D, C, B, and A. And you have your y-axis, which would be your ordinate, and these would be frequencies. So since I already made a line, I can do this. 1, 2, 3, 4, 5, 6, 7, 8. Oh yeah, there's one more. 9. Somebody scored a 9. So, and I'm going to make this a bit more F, D, C, B, and A. So this would be an example of the two axes. Again, you have your x-axis that corresponds with x values. So in this case, your categories of the measurement scale. Categories of the measurement scale. And your y-axis would respond to the frequency or score counts. In general, there are two principles that you want to follow. Both axes would have a value of 0 where they meet in the corner here. And the height of the y-axis should be about 2/3 to 3/4 of the length of the x-axis. So again, you would not want one that is too high like this, nor would you want one that is too low. Again, the general guidelines would be 2/3. So this is 1, 2. This would be 1, 2, 3, or 3/4, where you have 1, 2, 3, and 1, 2, 3, 4. So these are the ones you want. These are the ones you don't want for the height of the y-axis. So before you start drawing graphs, here are some questions that you want to ask. And there are 3 main questions. 1, what scale of measurement are you using? Again, depending on the scale of measurement, whether it is nominal, ordinal, interval, or ratio, you would use a different graph. Next, you would figure out what type of data you're recording, whether the variable is discrete or continuous. That also helps you determine what graph you use. And finally, a question to keep in mind is whether you are studying samples or populations. So the question is, which participants or individuals are you studying? And the answer to these questions would help you determine what graphs you would use. So in your next slides that you see, we're going to ask these questions and answer them to figure out what graphs we should use. So the first type of frequency distribution graph is called the histogram. Histogram. So the histogram is going to be used for a specific type of variable and a specific type of data. And when we see things to double check, these are the questions you would ask, and the answers you would expect are numerical scores, interval or ratio, and all of the scores on the x-axis are represented by the full range of the observed values, minimum to maximum. You want all the values and all the scores too. So, for example, if it was 0% to 100%, you would have all the values here, and then you count each person that scored that percent. 1, 2, 3, 4, 5, 6, and so on. So what would you graph and draw with this? You want to draw a bar for each score or interval. Again, the intervals could be individuals. In this case, if I were to do intervals of 1 for 0 to 100, that would not be realistic. But it could be, again, 0 to 9, 10 to 19, and so on, all the way up to 90 to 99, for example. Again, the height of the bar, you notice, though, corresponds to the frequency, not to the score. We're actually counting the number of people who got that score, whether it's a range or an actual number, or, again, the rounded little number of that limit. We count scores with the height. Y-axis is the frequency score, and X is the category. The width of the bar represents the score itself. Again, we keep the real limits because we are dealing with continuous variables. So for histograms, there's a couple things you want to be recognizing right away. Because we are dealing with interval or ratio values, there are points in between these values on the x-axis here, x and y. Again, y is for frequency scores. This will be your x-axis, so x is x, and the f here, the frequency, your score count, is the y-axis. And yes, when you see a histogram, the graph is saying that the x values are continuous. So you can have 1.1, 1.2, 1.3, 1.4, and so on in between 0 to 2. And you notice also that the bar itself, the left side of the bar, is the lower limit, the lower real limit of this value here. And the right side of the bar is the upper real limit of 1. So here for 2 it will be 1.5 and 2.5. For 3 it will be 2.5 to 3.5. 4 would have, let me draw eye on the point here. 3.5 and 4.5. And 5 would have 4.5 to 5.5. So the bars are touching. And that's something that would help you tell the difference right away between a histogram and a bar chart. The histogram have the bars touching because you're working with a continuous variable with real limits. You can also do group frequency distribution histograms, and the double check questions and the things to draw are similar to quote-unquote regular or individual frequency distribution histograms. Again, you would have numerical scores for your groups. Your groups are represented on the x-axis, and you count all the scores that is recorded in each group, including zero frequencies. For example, let's say nobody scored between 0 to 9%. Well, we include that too. Things to graph and draw, a bar for each group. Again, to remember, the height of the bar represents the frequency, that's your y, and the width of the bar represents the group, that is your x. So here is a picture of a group frequency distribution histogram. And here you have the interval, that is 2. Here the real lower limit is 29.5, and here the real upper limit for this interval between 30 and 31 is 31.5, and so on. There are possibly more scores here. It's not shown. But for the counts, you can see, 2 people got a score between 30 to 31, or actually between 29.5 and 31.5, and so on. And this is indicated right here in these frequency counts. So for one more, between 44 and 45 in your X value, only one person had that score. And this is shown in a group frequency distribution. If your counts are low and you can show each score individually, you can also do a block histogram. The next slide will show you this very easily and clearly. What this means that instead of having just a bar with just a shading and no blocks between them, and you measure that by looking at how tall the bar is, the block histogram shows you how many people are in each bar because you can count the number of blocks. And this is what it would look like. So for example, the X value of 1 has 1 person with that score. The X value of 2 has 3 people with that score, and so on. The highest one frequency would be the X value of 4, where there are 4 people with that score. And just in case this isn't clear enough, you can count like this. 1, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 1, 2, and 1. So you can still, and with block histograms, if the frequency counts are low enough, you can just count all the blocks and figure out what n is right away, how many participants in total. Even if it was not a block histogram, you can still calculate n fairly easily by measuring the height of each bar by the y-axis and adding up all those frequencies and getting the total that way. The disadvantage, before I go on to the next slide, with block histograms is that if your frequency counts are high, let's say you have anything 10 or over, you're going to have a hard time counting the blocks, let alone drawing them. So keep those in mind. Generally, we draw just regular histograms for continuous variables. An extension of the frequency distribution histogram is the frequency distribution polygon. So instead of drawing bars, now we draw dots at the highest point of each frequency count for each X value. And so when that happens, we draw the dots and we connect the dots from each one X value to another. And the dots would form a continuous line. Again, you can read the instructions here, but it is best shown with a picture. And I'll show you the comparison. Notice that the points themselves measure the height of the bar, if there were bars, and because this is a frequency distribution polygon and the points are connected, I would draw corresponding histograms because the values are continuous. Again, you would have upper and lower limits of this. And 7 is just 0, so it's like right there. So you would notice that yes, you can draw a histogram if you choose, but here instead a polygon is drawn. And what you do is you have the dots for the highest point, which indicates the count or the frequency, the count of the scores, and then you would connect them to form a continuous line. This is good for frequency distributions that have a large number of X categories. And if the X categories are large enough and there are enough, and the number of people are large enough, frequency distribution polygons is pretty much the only way to go, because drawing bars by hand or even on a computer would take extra time. And as you work with these frequency distribution polygons, and you can do the same with group frequency distribution polygons as well, you would start seeing, and I'll skip a few slides here, curves like this. This itself is also a frequency distribution polygon. A curve would show that, oh, there are many points between, let's say, 85 to 100 and 100 to 115. And this IQ test, for example, would be measuring thousands, if not hundreds, tens or hundreds, thousands of people. So if you had all these points, a frequency distribution polygon would be the best way to show that information. But before we get to curves, and just to review the group frequency distribution polygon here, you can see that, again, for your groups, and we can always do the real upper and lower limits for these for our groups, following the same logic. Draw that a bit more carefully here. So again, you can make frequency distribution histograms from frequency distribution polygons, or vice versa. Again, the more x values you have, and the more f's you have, more frequency counts you have, you're going to shift to frequency distribution polygons, and those polygons are going to look more like curves. So, we've talked about graphs for continuous data. What would we do for graphs that are measuring or showing measures of nominal or ordinal data? Instead of histograms, we use bar graphs. And the idea of bar graphs is that instead of using it for continuous scale where the bars are touching because there are points between the values like 1, 1.1, 1.2, and so on, we use bar charts because we're dealing with discrete variables that are nominal or ordinal in scale. What that means here in our points is that the bars have space because there's nothing between the values. There's nothing between the categories. They are discrete. And you can't measure the widths of the spaces or the bars for that matter. They're just categories of their own, whether they are ranked or not. And the categories, when they have no particular order, like this point says here, you know you are working with nominal data. When they do have order, conversely, you are working with ordinal data. Ordinal, think order. So here's an example. Personality types. Now, we're not supposed to say which one's better, type A, B, or C. By definition, they are distinct. And each one has its own personality type, and there's nothing quote-unquote in between, at least by definition. So if we use personality types as nominal data, and these are personality types, not letter grades, then you can see right here there's a gap between these. And there's no specific width for the gap, but again, within reason. And then you can count, oh, okay, in this quote, it could be a class. Okay, let's say we got 10 people with personality type A, 5 people with personality type B, and 20 people with type C personality. And again, you know you're working with nominal or ordinal data, in this case, nominal, because, well, 1, the x-axis tells us what kind of variable we're working with. 2, the bar graph tells us we're working with discrete variables. And next, we look at the categories themselves. Yeah, okay, yeah, even though it's A, B, C, but we're talking about personality types. And if you know about personality type theory that talks about A, B, and C, which was added later, yeah, it's technically nominal. So once we figured out and answer questions, what type of variable we're dealing with, what scale of measurement we're using, and using the right graph for it, we have some further guidelines as well. If a population is small, we will use the score of each person of the population to make a histogram. However, populations tend to be large, So again, drawing histograms, those charts of touching bars with individual scores is not going to be possible anymore. It's too hard. So we're going to shift to polygons. Instead, then we start using relative frequency. And then the polygons would become smooth curves to show that we're not looking at exact scores anymore. And so once we start looking at these frequency distributions that show relative frequency, and they're no longer bars or polygons but curves, and they're not showing exact scores anymore, we can start looking at shapes of the distributions rather than the numbers themselves right away. So we would note things like, hey, in a quote-unquote normal distribution, as in if we ask a person a question in the population, and we ask everybody in that population, and let's say, oh, how tall are you? And you can think of your height, and you ask the next person and they tell you their height, and you ask enough people, let's say in your hometown, home country, or Canada, and they start giving their heights, and you put all those in a frequency distribution, you count them and you graph them, you would see this kind of shape where there's an average height somewhere, and most people would have this average, but then as people go above or below the average, who are shorter or taller, there's going to be fewer people with that height. And you can see extreme people or people with extreme height, tall or short, that is not going to be as frequent. So you go, oh, wow, you're really tall. I hardly see you. Or, wow, you're really short. I haven't seen that many of you. Oh, hey, you're just like my height, assuming your average height. Then, oh, yeah, I see lots of people with average height. So this could be applied to various things. It could be applied to age. It could be applied to, I was going to say intelligence. I kind of don't want to, but it is. Even the IQ score shows that. But again, when you ask people a question and you measure them, generally, if you ask enough people in the population or just ask the population, you're going to get this kind of normal distribution curve, which has a name for it called the bell curve, and it has these properties. First, it's symmetrical with a peak in the middle because the scores pile up. And this is used as a common data structure for many variables. Again, ask any question that you can think of about us, whether it's our characteristics or our behavior. Generally, we could expect a normal distribution. And that makes sense for us. We have expectations about ourselves and about people that we can measure using statistical procedures. And we can make sense of the world this way. This includes our class. Oh, we would expect most people to perform at average. And if you do better in the class, again, in a normal distribution, that would be a more extreme thing. Just like we don't expect people to do really badly either. That's why we have words like exceptional, because we don't expect people, or don't expect everybody to do extremely well or extremely poorly. So again, statistical procedures, statistics and parameters, frequency distributions reflect these things. So here's an example of a bar chart with relative frequencies between bluegill and bass types of fish. And you can see here, oh, there's half as many bass that you would count than bluegill. So this will be an introduction to our normal distribution, looking at relative frequency. And this is what we see in the next graph. So notice in the y-axis now, where we don't have actual numbers, but we have relative frequency. And again, remember the proportion thing that we did with your p, and then that's equal to frequency over n? Yeah. So this is relative frequency in that sense. So if you see here, this is twice as high as that, then you could say with relative frequency that twice as many people score 100 IQ than people who score 85 IQ or people who score 115 IQ. Let's say in between here, this would be like let's say this is 1/1/2. I'm just arbitrarily saying this is 1. And this will be half of that number. And this will be 1/4 of that number, whatever that is. You know what? I'll just name it X. There you go. So 1/4 of the people, if it was, let's say, if we asked 100,000 people, then it would be 25,000 people. If 100,000 people tested, and it's probably more than that. I'm just thinking 100,000 people scored 100 IQ. Let's stick with that. And if 100,000 people scored here, then this would be 50,000 people scored either 85 or 115. And then if it was somewhere in between 70 to 85, in between that number, it could be 15. So 77.5. So this would be 25K and on both ends here. And then if this was like 1/8, then, this would be 12.5K. So again, we're talking about relative frequency. So you will notice right away that this bell curve would have the most people in the middle, in the average. And this normal distribution is symmetrical, that you would expect, okay, the score to pile up in the middle, and then roughly the same number of people in descending frequency to score below average, and roughly the same number of people, again, in the same descending rate of frequency to score above or below. And again, another name for this is the bell curve. And a practical thing here, when you hear in courses instructors or professors scaling the grade, they are placing your grade on this bell curve, figuring out the average of everybody's grades, and then putting people above and below average and assigning letter grades or percentages to that, because they're trying to make the scores, within expectation, or putting the people in the class within an expected or quote-unquote normal distribution. This would happen, for example, where if everybody scored between 90 to 99%, and the average would be somewhere between, let's say, 95. And so in that case, then the people who scored 95 would be in the middle like this. People who scored 99 would be at the top, and people who scored 90 would be at the bottom. Again, you don't want this, neither as a student or as an instructor, but if it must be done, that's how it's done. So if you hear any courses that go, oh, hey, is that course scaled? That's what it is. That's what's happening. So, but there is reason for this. And that's because for people on this planet, when we behave and do certain things, and we ask the question and we measure enough people, this is the distribution we expect. That's why it's called normal. Again, review, there could be use of graphs that can be good or bad, as in use and misuse. Generally, how you scale the axes can totally change the shape of the graph. So for example, here is a serious thing of a count. This is the number of homicides. That's the number of people killed. If you count individual scores and scale them quite high, in the sense that you're spreading them apart, then you can see, oh wow, the increase is really huge. Even though it's 2 people, it looks like the curve is really steep. Again, of course, being homicide, 1 is too many. But looking at the graph, it looks like the rise or the slope is huge, even though you can still calculate the slope with the slope formula, and you can try it to see what the slope actually is. So 1 year is increased by 2 people, or somewhere between that. Actually, 1 year has increase from year 5 to year 6 is 2 people, and then year 6 to year 7 is 3 people, and then year 7 to year 8 is only 1 person. But if you use a different scale for your frequency count, and just, instead of intervals of 2, you use intervals of 20, the slope no longer looks as steep on the graph. Again, you can always check that with actual numbers. So this is a good lesson for looking at data not just on the graph, but also with the frequency distribution table with actual numbers. So when you look at data, you can make more accurate interpretations. And this applies to anything. It could be your spending. It could be your consumer behavior, as in what you buy or how you review stuff. It could be if you are, paying attention to what you eat or how much you exercise. Yeah, you have fitness apps that show graphs and stuff. Again, you can always check your data. And this knowledge that you're learning from can apply to these things. It also can be applied to your study habits, how many hours you're spending. For example, if you want to, show a more accurate result, you can measure in minutes instead of hours. And, if you use days, it would start to look like this. And this would be another lesson about time management. But again, this applies to a lot of things, including time and numbers and so on, as well as money. So the last bit here, we're going to talk about the shape of the distribution, or the shape of the frequency distribution. This would be one of the highlights in our virtual class or class. And so when we talk about the frequency distribution shape, we can talk about actual frequency distribution histograms. They have shapes. We can talk about regular frequency as in individual frequency distributions or group frequency distributions, bar charts, histograms, polygons, or curves. They have shapes, and we want to describe those shapes because they give us an overall summary of how people do, whether it's behave or perform or some characteristic. Again, we already looked at one of these categories, symmetry. Here you see a curve that is symmetrical. So symmetrical would be if you split the distribution in half, part A looks the same as part B. It's like a mirror image. It's symmetrical. Left side is the same as the right side. But what happens if the shape is not the same? So here, for example, this is not symmetrical. If I split this in half, A is a lot smaller than B. Same as this one. It looks symmetrical, but it's not. And there's also a sloping shape like this, even though, again, they can be misrepresented. But yeah, this has a skew or a tail. This one has a negative skew because the values go down to the bottom and it looks like a tail on this end, whereas it looks like a hump on this end, or a peak. So when we describe these characteristics, when we look at graphs, we start to describe the shape of the distribution. So let's take a look at some of the notes here that would tell us how to describe them. Again, we make frequency distribution tables and we draw or draft these graphs. And once we look at the data, whether it's looking at the distribution table or a graph, you can start describing the shape. Of course, with graphs it's easier because it's a picture. It's easier to describe pictures. There are sayings for this, like a picture's worth 1,000 words. But if you learn to look at frequency distribution tables, and I just made one like this, I'll use numbers this time, you can still make the same conclusions if you know how to look. Oh, well, the middle is 3, x equals 3, and it has 9, and then it sort of piles up like this. And it's still symmetrical because the numbers are the, oh, sorry, I'm supposed to say they're the same. Yeah, there you go. The upper half and the lower half are the same. So you can start describing it like that. Symmetrical distribution means one side is the mirror image of another. I'll redraw this one. Like that. Okay. A skewed distribution, you can have two types of skews, and I'll draw one on the left and one on the right. So a negative skew or left skew would have a tail on the left. So this is left skew. And think here skew is tail. And you can have right skew, where the right side, the positive values, would have fewer frequency counts or fewer score counts, and so there's a tail here on the right. Again, I've mentioned before in the previous chapter or in the class that these shapes can also have plain English or practical interpretations. Like if you see a symmetrical distribution, you say, yeah, it's expected, or it looks normally distributed, especially if there's a peak in the middle. If it's left skew or negative skew, that means the peak is in the positive end, and you can say, oh, it's too easy. There's a floor effect. Oh, most people would do really well. Whereas a positive skew means the test is too hard. Not many people score so well, and most people did not as well. So there's a quote-unquote ceiling that you can not pass for most people. So again, symmetrical means one side is the same as the other in the distribution. A positive skew is on the right side, a right tail, if you look at the frequency distribution curve. And the skew means tail. That means fewer people score that value. Okay, and negative skew is left skew or left tail. So here are the shapes. Again, this is picture form. We've used words to describe these. These are symmetrical. Again, side A is the same as side B, left the same as right. When they're not the same, there are only two descriptions really. And notice the line I'm drawing here is not the middle line per se. I'm drawing the mode, the most frequent score, and we're going to talk about this very soon. Here, positive skew on the positive end, you have the tail, and negative skew, we'd have the tail at the negative end towards the negative direction of the frequency distribution. So I think that's it. We're done for the day in this chapter. Yeah, so let's go with these questions. Number 5, what is the shape of this distribution? Pretty easy. If you said positively skewed, looking at the tail at the positive direction on the right, you're right. And number 6, 2 true-false questions. A, it would be correct to use a histogram to graph parental marital status data, that is single, comma, married, comma, divorce, comma, whatever, separated, common law, whatever, from a treatment center for children. True or false? B, it would be correct to use a histogram to graph the time children spent playing with other children from data collected from the same center. Again, is it right to use a histogram for these situations? The first situation being marital status for their parents, and that's a particular scale and a particular type of variable. Or do we use a histogram for time spent? Again, that would be a particular type of variable and on a particular scale. So for the first one with marital status, because it is a nominal scale with a discrete variable, again, by definition, you would not use a histogram, you use a bar graph. And for B, yes, you would use a histogram because time is a continuous variable on a ratio scale. Ratio being, well, time spent. The child could spend no time playing with other children. Sad, but it is possible. So there you go. This is it for our chapter 2. At this point, we would have covered all 6 learning outcomes. And if you have practiced these questions, not only on the video, but also on the textbook, we have already covered the first 3. So the second part of this chapter, we have covered how to interpret, how to describe and talk about, discuss these frequency distributions, be they group frequency distributions, individual frequency distributions, on various scales. We can do that now. We can organize these frequency distributions into graphs. We talk about the axes, x and y axes, x for the values and categories, y for the frequency count. We can do this either for individual categories or grouped categories. And number 6, we have explained how to identify and interpret these graphs, especially the shape of these distributions. And as we lead on to frequency distribution curves, for example, the bell curve, which is a normal distribution or a distribution that is normally distributed, that is symmetrical with one peak and has the same, the same left and right side. We also talked about positive skewed and negative skewed. Okay. We also talked about briefly bimodal distributions. I mean, if the distribution has 2 peaks, it's 2 modes. We will talk about mean median mode in the next chapter, which will help us further interpret and identify frequency distributions, be they graphs or tables. So that's it. Again, I will remind you basically every class, if I have to, that doing these videos is still no substitute from working in a textbook in this class. And when I say working in a textbook, I don't mean just reading it. Just like I write on these lecture slides to show points, you should write in your notebook or even on your textbook if you printed it, or on your screen or whatever, whatever writing tool you have to work with these materials. You can't type these questions. You must write these by hand. If you happen to be using programs or websites to do these calculations, you're not doing any work. All you're doing is inputting data and letting the program calculate the results. To understand and apply the logic applied in these statistical procedures, and to use the mathematical formulas and calculating values and achieving these outcomes, you must write. You must draw on paper, or if you have gadgets, then on a stylus and tablet device. Again, writing is thinking, and this applies not only to papers but also to classes like this. So use the videos to listen and learn if that's your preferred style, but still use the time, plan extra time to work on your textbooks. So these are your 6 outcomes. That was chapter 2, parts 1 and 2. If you have any questions, you can go to your textbook. That covers each part in even greater detail at your own pace because you can read the textbook. You can also pause and go back to the videos if you need to. Again, if you were to take breaks, go by the 2.4, 2.5, and so on. You can also email me directly and ask me questions if you still have questions at that point. So that's it. Keep going. You can do this. Next time is chapter 3, and we'll see you in the next one.